System. English. It's not everything. Who is waiting? What was coming? Good morning. Now I can start 100%. 100% sure I can start my lecture. I thought this one will be good for today. This one. But then someone told me that it's not very good for calm. So, what's for today? One of the tasks with EOVITS is a search for optimal, best, most profitable. Good example of such task is something like this. You have a network. It's a network. You supply clients. Here are your clients. You have, I will take for example two power plants, number 1 and number 2. Your task, this is a thermal power plant. Okay, it can be any, but for example, let's say they are thermal. So, power consumed by load is less than P maximum 1 plus P maximum 2. You have a power surplus, capacity surplus. So your task is select or regime or distribute load to obtain max profit. Yeah. For power plant, we can select two modes, PU or PQ. PU, our dispatch. I have a big stars here. Okay, middle stars here. I can call the power plant operator guy. I need megawatts and megawatts. This will be PQ, or I need you to supply megawatts plus keep a voltage absolute value. It will be PU. P, here I have power plant is changed by amount of fuel burn. For hydro plant, amount of water flowing. Voltage or reactive power is controlled by excitement current. So for P, for active power, I will, for each plant, I will have N P maximum I, here I from 1 to number of power plants. Oh, this one, of course, it's a mechanical strength, it's maximum pressure. Boiler can withstand and so on. But why I have this one? When we take real power plant, what we can find? We can find steam turbine, we can find gas turbine, we can find something like diesel engine. For diesel, for small diesel engines, it's near zero. For gas turbines, they came from aircraft industry. Efficiency chart is what in effect efficiency. In reality, it's a fuel consumption per 1 megawatt of produced power. Looks like this. Efficient, deeply inefficient. This will be approximately 30%. They are extremely inefficient on a low loads. They simply burn fuel and they lose efficiency 105%. Boost regimes are extremely inefficient, 2 times higher fuel consumption. So it's an efficiency, something like this you will see efficiency chart.
Professor, it's a fuel efficiency or the generator efficiency?
Yeah, it's a fuel efficiency, it's amount of fuel per 1 megawatt. It's a B. For steam turbines, is a bit different situation. For steam turbines, limiter is a steam flow through the low pressure stage. It's determined by thermal load of the low pressure stage. For small turbines, it's not so vital, but for large power, low speed turbines, for turbines with heating, this heating diverts from the second stage, it is vital to maintain minimal steam flow through the low pressure stage. They are like this in diameter. And with very small tolerance, any disturbance in thermal regime may lead to mechanical damage. Do not mess with turbine gas. Usually they low in height, quite, how to say, they have kind of strong constitution and they are very short to, how to say, teach you with their fist. Beware of turbine guys. Sometimes they are very short and straight how to explain you what this regime is not welcomed by turbine. Okay, so same thing is with the reactive oil. You can see chart like this. 1 second, it will be, and here will be cosine. Chart like this, it's a limiting chart. This arc is set by allowable generator current. Max, this is capacitance. This part is limited by rotor current, by excite. This is, and this part is limited by, I'm asking, you know it. This part is limited. Why this line? What's the limiter of this line? This line is set by generator stability. If you drop excitement current below this margin, moment synchronized will be too small, and your machine will make an asynchronous turn, meaning huge mechanical load. It will be, it's sitting hard. This is not welcome. It's very dangerous mechanical, because your machine may lose this magnetic coupling and make an asynchronous turn. It's a nice way. For example, you can break coupling between turbine and generator itself. On hydropower plant, you can get hydraulic heat and lose the main wheel of your hydro generator. Meaning year of repairs. I'm sure what your next job will be garbage collector. If it will be your mistake, your next job will be garbage collector. So paint this line in red and obey this limit. Failing to do so, really, year of repair and multi-millions. Now, what I'm willing to do? I took a two-machine system for simplicity. I'm not able to draw multi-dimensional charts. So I got limits I can draw on a plane in coordinates active power, reactive power. Here I can write one thing. What are power consumption on my network? Where the power goes? One part I'm selling to clients, yes? And there is another part. What? Losses. Losses. Yes, I need not only to supply clients. Is part what I will sell to client, and is part what I will lose on transit. If I ignore transit loss, I may get wrong decision. I can choose more. There is a problem. This power plant may be effective in that one, but transfer losses I need to cover equalizes them. So I can write an energy balance equation here. One of the station will perform a balancing role. It will be select bus. For I can assume that select bus on base node, what will become a base node, this station will cover the network losses. It's someone need to do it. So I will assume that second station in my I have two station system. Someone need to close the energy balance. Sum of energy should be 0. We cannot store it. As much we somewhere, as much we produce, as much we sell plus transit losses. So I'm writing what P2 is P load plus I will sorry zud no Latvian zudumi. It's a losses. This one is load and this one is network losses.
Someone is on.
Who is knocking at my door? Who is knocking at my door? No? А кто кабель? Я так сказал, кабель луку, а что? Так. Nu secunde. Nu pievienot, varbūt tikai melnās. Pārēc es atcelēju. Lai atcelētu, vajag ceru pēc tam uzkāpt uz skāpli, nolaist kaseri, un tad būs piekļuve. Ja viņi gals ir kontrolēt. Viņi tagad, vispār var pamēģināt, viņš tagad, ja paliec tā kā ir, visas cīsas izņemot melni, iesot uz zemi. Var pabaudīt, vai uz zemi vispār. Man tas sajūt, ka viņš ir melni. Tā, ko es esmu, ko es daru? Okay. This one is to give minus. If it would be many generators, will be balancing. I will mark it. Okay. All load plus all losses plus sum of all generators.
Maybe it's a plus or minus?
Yeah, this should be minus.
Minus, yes.
This should be minus because it's so balancing node covers all losses, all difference. It's close the balance, like in accounting. This one will be last line in balance. Same thing with the reactive power. All load plus all we need to network minus first, or in general sum of all other machines. Here I will use index 1 because in my system of 2 power plants only one is freely selectable. The last one is not independent. The last one comes from the energy balance. If I have 10 suppliers, 9 will be free and number 10 balancing not. Here I can draw a lines. Minimum allowable reactive power, minimum allowable reactive power for the first machine. Minimum active. What I receive? This rectangle marks area of possible solutions. Solutions outside of this rectangle are not possible. In reality, when you take a real power plant, there may be more complex limits. Possible you will have not welcome. With hydropower plants, usually there are areas, okay, you can use this area, but only for 15 minutes. Because it's, what it's? It's an area of dangerous vibrations. Cavity problem, vibration problem, or possible overheating problem. So for hydro plants, if you will operate a real hydro plant, you will have chart like this. Nice. It's a water level difference, opening of guiding apparatus, and nice gray cloud. Maybe multiple. This area is not welcome. It's a articulated vibration area, or danger of resonance. Or so you can pass it, but you cannot operate in this gray area for continuous time. If not, it will go out of possible solutions.
Professor, in Latvia, the weather condition is changing continuously. In which time the losses, the transist losses is very low compared to winter and summer.
No, losses are dependent on load. So winter load is higher, losses are higher. But for us, not losses is the main factor. Main factor is water availability for hydropower plant. It sets economy. In summertime, water is enough only for a couple of hours of operation. In spring, or during the kind of rain season, it's enough to maintain operation whole day. Water storage, water reservoirs are insufficient to hold water for months. So economy is the main determined by water, not by weather.
In
So,
the same condition, the transmission line.
but we don't, for some countries or regions, very painful moment is air temperature, because air temperature sets the possible current limits for transmission line. So less effective mode should be selected to avoid overheating of line. It's not our problem. We don't face line overheating problem. Okay, let's go back. Nice chart, isn't it? I can try to show idea in 3D. Let's say this is active power, reactive power, profit. Or I can use not profit, but another word, fuel consumption. I'm speaking on thermal plant. If I draw fuel consumption, I don't know, maybe like this, something figure like this, it's a fuel consumption as a function of active reactive power. I need to find best one, most profitable. Here it is. But how? How can I do it? I need to find this point. I have, for example, like this. This is area of possible solutions. So, this max profit means minimum fuel consumption. It's somewhere here. But how to find it? Oh my god. We got clone online. 1 second. What I'm trying. How can I get this point?
So many processes.
And I keep in mind, I should keep in mind. What? What I should keep in mind? I should keep in mind I need account all losses. And that's not all. Any possible regime I choose should be realistic. And to be realistic, I need to fulfill limitation, not only for my first machine, but for second too. For all generators. I cannot overload balancing station. In theory, if there would be no losses, I can find this point via system of partial differential equation. But I have to account losses. So, one of the techniques used for such task, it's not an easy task, it's a complex task. Hard task, in reality. It's called Monte-Karlo. Monte-Karlo is a place where people are playing cards, roulettes, and all kind of prohibited games. What can I do? Hop and draw. I can generate a random number. I can select random one point here in the area of possible solution. Let's say this is point 1. I need to compare it with the best, but first, what's the point 1? Point 1 means P1, Q1. I generated it random. I have point, randomly generated point. What's the next? Next, I need to perform a losses calculation.
Because maybe we got B and P are under middle points in depth. this x, y, z axis.
Yeah.
Maybe we got x and y in the least middle one.
Yeah, but how can you find it? If there would be no losses, you can use gradient to get.
Yes, yes.
But losses make this function, you cannot obtain derivative easily. To find this point by meaning of equation, you need derivative. You need to construct a gradient. It's not easy. Actually, it's not feasible at all. When you start to dig deeper, I started from station of one machine. If you have group of machine, you will have interruptions. At the interruption point, derivative will throw you to infinity. So here I need losses. How can I get losses? With one of the way, apply technique of inverse matrix to the network. Next, I need to check if P2, Q2 are within allowable limits. If not, there is no sense to go further. If within limits, I need to calculate fuel consumption from the fuel consumption chart and then compare it to is it less than with the best one. At the 0 point, best one should be infinite, so anyone will be better, and then for each test I will compare my fuel consumption with the best one. I have one try, nothing to compare, it will be the best. So this will not work, this will work. I need to calculate precision and here also I need to save the best one. If so, I can return back. I can throw once more. Get the number 2. I get number 2. Oh no, and success, this will go this way, not better. Throw once more. For example, here, number 3. 3, okay, here, for example. 3 is better than 1. It will be the best. It will take the best. So if you see, we are throwing, and some of the tests are better, give us better and better results, and after some time we will be near to this point. Looks like a brute force approach, yeah? In reality, it's one of the most effective for such tasks. It sounds ridiculous.
In this picture, x, y, z, 3 axes, I need this point, the same.
Yeah.
So, if I need to calculate y, if this is x, y is the x, y axis,
Zits man spробує. Labi, man lekcija. Yes, but you have your problem is linear.
Oh, yes, linear.
And this is problem linear.
Curve, okay.
Curved with interruptions. It's not simple curve. It's not a second degree problem. It's with interruption. Don't bother. I knew what I'm speaking about. That's not all. This one is simple. More general problem. When you have something like this. This one is called global extreme. And this one is a local extreme. You can try to conduct a gradient solution. And gradient solution will easily struck in local extreme. This technique, first, why this technique is effective? It's quite hard to explain, but have you seen this Invisible Man movie? If you throw a water on Invisible Man, can you tell exact mass description for him? No, but you see water drops. And water drops give you quite a good impression on its, let's say, shell. Same thing. It's proven. It's proven relative to military operation. It's in 40s proven. But if you have more than 3 independent coordinates, this is effective when attempt to solve it directly by mass. Finding a point in cube is easy, but this surface is not a cube. It's not even a second degree surface. It's a very complex surface with not welcomed areas. For not welcomed areas, it's very easy here to do one thing. It's very easy to implement a strafe function. If you trap in non-welcome area, just add fine points to your fuel consumption, and it will work. Or you can calculate in money units, easy. Add a fine to your money unit. This technique is real solving a problem. Why at the first approach it looks dumb? I'm just throwing. In reality, it's very effective. You just need uniform random number generator and ability to solve direct task, to find a profit as a function of point coordinates. It's more effective than try to draw a net or something like this. Yes, it has a problem. If you will get first approximation very fast, but if you need a high precision, you will face a problem. Most of the tries will be useless. That's why modify, if there is a, let's say, matter of performance, more target-oriented approach can be used. For example, Wolfpack approach, when at first Wolfpack members seek randomly, and if one wolf finds a prey, finds some extreme, pack goes closer and starts searching in the neighborhood area. But at first, I would say 100% guaranteed. Monte-Karlo is safe. Monte-Karlo can deal with very complex target function. Monte-Karlo do not afraid of interruption. If, for example, you have two power plant of two generators, one chart up, second, you can have a very complex task. For example, you have a large hydropower plant. Yeah? For large hydropower plant, there is one small problem. If machines closer to coast work with full load, water level at the middle of the river rises, and machines in the middle lose their efficiency. You can solve it, such task solvable with Monte-Karlo. Thermal plants with heat recuperation solvable with Monte-Karlo, because you only need to define fuel as a function of power. Okay, maybe I can show how it looks like really. I would like to show it so. Maybe possible. I would like to show it so. Where is my silver? Something not working. Why? Or oh, now it's okay. Now I can open this. Optimization of station or flash one. Let's go. Let's try to understand how it works. This part, Jordan, it's a function familiar with all this. It's from our, not the previous, it's from one before. It's a function to obtain inverse matrix via Jordan process. I need to find losses, so I need power flow. That's why I will incorporate our, not previous, task number 8 here. I use schematics from the this previous task, just not to see, for simplicity. So, as you remember, it has 6 lines. All its active resistance of 0.21 ohms per kilometer and reactive 0.49. It's 110 kilowatts lines. Resistance matrix, and here is my topology. I just copied from our previous task. Number of nodes, number of branch, loads also from previous task. Here I put something. It's just a plug. I need something to fill the power vector. I will put a real number later. Voltage of the base node. Now here, this part. For machine, for generator, I have a nominal power. Rated power, 100 megawatts. Okay, good. Also, I will receive this value. It's a rated power factor. But the best one for this machine but also from manufacturer, I should get these two digits. They are setting limits on reactive power. This one is for capacity, and this one for overexcited machine, underexcited machine. I should get the in some or as a limit of current or as a limit of power factor. Manufacturer of the my power plant, I should get a paper elaborated by. From these digits, I need first I calculate full power or apparent power, and with these two nice formulas, I'm getting in real values, in named values, maximum allowed reactive power and minimum allowed reactive power. This one is limited by excitement current, by thermal regime of rotor. This one by stability. Also, I should have from its station, usually they are not from manufacturing, they are from commissioning. There should be, this one will be from manufacturer. Max allowable active power, allowable overload. And this one minimum is, usually it's in commissioning paper. Maybe for gas turbines, I sold this in manufacturing papers. They give a nice efficiency chart. They performed a commission test before company did it, and in commissioning report from the it came from construction company. Here is your efficiency chart for your generator. Same for the second machine. For all plants, I need maximum allowable, minimum allowable. Okay, next. These are totals for load. I just calculate from, since I have a vector, I need to know gross sum of active and reactive load. Conductivity matrix of lines. This moment. When I conduct a power flow, at the first moment I don't know anything. I can assume what nodal voltage will be somewhere near the base node voltage. Base node voltage, I cannot choose anything. I'm limited by a net code. I can go up from 10% and down 5, something like this. It should be somewhere in national code, but okay, I choose 150. Actually, it's a separate task to choose a base node voltage or setup for voltage control system of my network. It's a separate task. At the first hand, the higher voltage, smaller losses, small transmission losses. But on the other side, if you raise voltage, this means what steel losses in steel of power transformer rise drastically. So I need in reality good power components perform a research what is the optimal level of voltage in the network. It changes in small, let's say 15% area, but it's a task that can be solved. If you need to tell something, why you need to employ me to some bosses, tell, I knew what you have a problem with best voltage level of your network. Maybe this will help you. do I solve such problem? It's how to say, they offered the salary they offered was too small. So I sent them search for money. I knew what to do, but I will not do. I will not raise from bed for such salary. Okay, let's go forward. Nodal admittance matrix. Here in such test, it's one important moment. I warned about it. Network do not change. Change only load. That means if I already solved the linear part of nodal voltage problem, non-linear nodal voltage problem, I will get I will boost performance. To do so, I apply Jordan process to my nodal admittance matrix. This is said to make random number generator to produce uniform distribution. I can do a trick, I don't like it, but if I knew approximately where the solution is, I can switch from uniform to Gaussian distribution, like this. To avoid testing whether there is no solution. What was the name of senator? I prefer to hunt ducks where the ducks are present. So I prefer to search for solution where solution is present. Okay. Main precision and best consumption of fuel. Until I don't know anything, I set a very high consumption. It's a dummy. It will be replaced. Okay. And number of tests. While this thing is clear, while precision is not acquired, or I don't, but I have another. This one. See, in my practice, there were rare cases when two random numbers fell one in proximity of another. If I value precision only by difference between previous best and next best, it's a rare case, but it can happen. I can falsely detect, I'm in the vicinity of best solution, while it's only a glitch of random number generator. To prevent such case, I make 100 tests unconditional. So there always will be 100 tests. And later, only later I will check for precision. These two, you can see it's a generation of random active and reactive power for the first plant in the area of possible active reactive power. Here I create a real power vector, calculate this I don't need full matrix, I need only main diagonal, and we already saw it. It's a solution of nodal voltage system with the inverse matrix technique. I will get branch currents. I'm not interested in power for RST. I need this part. Calculus of line losses. I need this. That means Zudumi copper total losses of network. And for second machine, for balancing machine in my case, I add real and imaginary part of total losses to its active and reactive part. here is the check. If such a regime is possible, such mode possible, will the second machine bear my load? If not, try once more. If acceptable by active power, I recheck for reactive. Possible? Okay. I use the it's from the testing machine real such nice polynomials. First one are from PowerPoint commissioning, from testing. Actually, now when you order a PowerPoint project, design company, will perform approximate tests with something like gas cycle and thermofor. They will give you efficiency chart, expectable, but real are coming from commission. Station should be checked for full load range and signed and sealed document. Construction company, your project company, gives you a report. We build, it's a commission report, we built what you ordered. Our efficiency is, let's say, we fulfilled order. Here's your efficiency chart. It's bad, okay, it's not worse when you order what design company promised you. You will have, it's a fuel consumption as a function of active power. In my case, it's from some old power plant. You will not get it as a ready-made polynomial. You will get a table, test table, and nice chart approximated with the polynomial. Take an Excel and do it. It will be your job. They will, in the commissioning paper, you will have test chart. Sometimes commissioning, okay, it's commissioning, but station worked a bit, maybe something worked, and so on. For historic data from control system. Sometimes before solving task, we spend couple days in this control room taking a historic data from control system, something like CMS. Oops. And compare it. Sometimes it's funny to compare it with commissioning chart. What's the result? Yeah, result may change. Efficiency may go down. Components were also one of the problem in gas flowing path and so on, maybe some residues blocking gas flow and this lowering the efficiency. It's possible. Okay, what's the next? Total consumption of fuel. If total consumption is better than the best one, we save regime parameters. We'll calculate precision as a difference between previous best and next one. Yeah. And put it here. Actually, maybe it's more correct. Put this one here. Okay, out of limits. When precision is reached, I only need to show best fuel consumption, number of steps, active reactive power for the best one regime, and pseudo-Mikopa means total losses. Yeah. Maybe I can try to run it, what I'll get, thinking, stop thinking, start counting, machine, come on.
Any iterating?
Something, where are you?
It's too late.
What's too late? Oh, send admission for bachelor. This guy pretends what he is pro in electronics and liquid mechanics and so on. Funny questions, isn't it? Who can answer? What's a natural logarithm minus 1? It's a captcha for bachelors. Natural logarithm of minus 1. Very well working. Okay, what's here? Something went wrong. Hey, machine. Okay, I'll do it in brutal way. B, brutality.
So,
What's going on? Ah, yeah, now finally. Finally. So I need this, I need to run and what? Oh, now works. It was a glitch. Take a look. I attempted to solve, got several impossible attempts because reactive power of second machine was out of limits, and here I got best regime will be achieved if I put 108 megawatts to the first generator and 26 for the second. Losses 6.42 megawatts. For example, take a look. I'm changing. I will make second machine more effective. Calculate. Oh, 91.42. And losses. What's about losses? Previous one, where are you? $6.42 here. In this case, 4.81. But anyway, in 100 steps, 108 fuel consumption. In previous case, where we was? $1.10. Maybe let's make it less efficient. Now second machine is less efficient. Oh. It's not easy. Lot of unsuccessful tests. I need to fulfill limit of, yeah. See what we got here. First one will take almost full load. Second one not effective. And if first one is less effective. In 100 steps, 84.48. Fuel consumption, 115. It's tons an hour. Real unit here. It may be in per joule, but in reality it's ton. Ton per hour. So you see, it's easy and effective, and can work really with very complex target function. Very complex. In reality, it's a very powerful tool. Oh. 89.29. Nice toy.
Yeah.
But it's, in reality, it's a way how to bring your boss good news. For larger system, you need a larger network model, but general core, it works. If you have lot of power plant, task will be a bit different. So bigger computer or targeted, let's say more target-oriented approach, but also kind of way one of the random searches. They work, I'm sure. Okay, maybe some questions. Huh? 0 years. He is coming. Tell me, BTV, one thing. What you...
This is X, Y, Z axis.
Yeah.
I need this point.
Possible.
X, Y, Z.
Yeah.
Axis. I need the intersection.
You need intersection point.
Yeah.
Intersection
because
point.
if I find the intersect points, this point is very easy. In this graph.
Yeah, extreme is very easy. One of the approach, there is one moment. You have 2 points. Which one you want? But
I need exactly maybe this point, because there are 3 axes.
Yeah.
X, Y, Z. I need this intersect point.
Yeah. On the one hand, you can try to solve configure an equation system, since this in this direction it's line. You can solve a flat task of system which will yield this two intersection points. But you can do it in opposite way. You can apply optimization Monte-Karlo to minimize difference between them. You can solve a task like you can define first. You need to split your task into. No, you need to split your task into. See, if you want this in 3 dimensions, result will be not one number or one digit or one something. Result here will be area. In reality, it will be space for your task. Your space reduces to 2 lines, but this line is an infinite. You will get space. If you want only intersection point,
just I need the intercept point, because in this graph, the same happen. If I need this point, if I find out, it's very easy. In this point also, it's find very easy. If I find this is very easy. In this curve.
No. This curve is, I just draw it as a curve. See, if you ignore net losses, it will be nice second degree curve, and you only need to solve a PDA. Just take a derivatives from the fuel consumption chart, write a system dB by d power equals to 0, and you will get immediately best one. But if you ignore losses, at the point you start calculating your loss.
This is 3 axes.
Yeah.
I need to convert first V and P separate X, Y axis. Then I find this point. If I find this point is very easy in the 2 dimensions, X and Y axis. Then after I find
but your task has as many dimensions. 2 number by 2 multiplied by number of 3 power points.
It's very good, Professor. I will tell you. If I convert
if you have 10 power points, you will have 18 coordinates.
Like this?
Not like this. One power point gives you two coordinates.
Maybe it will be intersect this.
No, you can change freely. Imagine you have 3 power points.
Okay.
How many power settings you will have?
3.
Because one is balanced.
One is balanced. Okay.
2 for active and 2 for reactive. And they are independent. You need to draw for the 5-dimensional chart. Each power point adds 2 coordinates.
It is possible to compare the three power plant with this graph, and I make the intersect points and the three graphs is a x y axis. Then I finally I got this like this. This is power plant one. This is power plant two.
Yeah, it's a consumption.
Yes, only in this chart I find only these two values only because I need this point value.
At this chart, you find in this chart PQ are in lower plane.
Oh,
You seek in this direction.
Yes. I find one of these tags.
Yeah, so you need PQ for best point. For this corresponding
If I
to this
find
point.
this point,
Yeah,
this point is corresponding is very
if there is a tiny or one tiny word, if, because this figure, yes, you can do some funny one. You can try to approximate, calculate some points for reality, some point of this. Try to, using this point, try to create this figure. Try to, with regression analysis, to find a real curvature. It's a...
Professor, I have another graph. I show you another graph. Maybe this. Yes. Maybe this is a good graph. Okay.
Looks like something from Fourier.
Yeah. I can copy this. And I'm going to copy this. Professor, if we can imagine it's a z-axis in the like this, I need only x and y axis. I need this point, maybe this point. If I select this point, I got the value. It's not a matter. If I find this value, this is a z-axis like this, same like that. So if I find this value by this graph, then I can also find a z value also according to this point. It's
Yeah, you can, but what will you find? What's this graph?
Upon,
it's a sum of them?
Yes, it depends upon x and y point, middle point, I find out. Then this is this is perpendicular to the z-axis.
Yeah. Can see, to find extreme for uninterrupted function, you need what? To get a derivative.
Maybe some point, some values.
But try to get derivative from the losses. The problem is what you cannot easily get this derivative. If it would be uninterruptible surface, and it would be possible to construct a gradient vector. Remember the gradient?
Yeah, it's a gradient. A gradient vector.
What's a gradient vector? What it shows to us?
Maybe I had a gradient vector.
ITM. What's a mass definition for gradient?
You mean it's an angle or?
No. If you take for example, you have function from let's say x1, x2, y is a function of x1, x2. Okay. What will be gradient?
Maybe it's upon the axis.
You take a partial derivative of
maybe
y by x1
x1 and
x2. It will be vector showing you at the particular point, showing you the growth direction of your function. Anti-gradient show you a downward direction.
Okay, I understand.
So if you have an interruptible surface and you can construct a gradient, you can use a gradient. It will show you direction to the extreme point. You can write a partial PDA, partial differential equation, system equal to 0, it will show you extreme. But the key problem, you need to be able, you must be able to construct a vector of derivative.
Professor, if I imagine
matrix.
this is a x1, this is a x2, I can imagine.
Yeah.
Is mean I need a gradient value of x1 and x2.
You need the gradient value of the function. Function from x1, x2 at some point. It will show you direction of growth. Take it with the.
Yes,
if you're seeking for profit, it will show you direction to the most profitable.
Yes.
If you take it with minus sign.
Maybe this diagram is a help for that.
I'm not sure.
Yes.
No.
We have four.
For example, in theory, we are here. Any gradient will show us
That point, yes.
point. Go here, go up, at this point,
This point, yes.
it will direct you here.
Yes.
But the problem, gradient techniques may converge to local extreme.
Okay.
It's problem number one, but the general problem, what will be gradient if you have 1, 2, 3?
Okay, it means maybe intersect by this.
You need to approximate it. Because on the other hand, in the moment you have one machine, it's run. Now it's time to put a second.
Second, yes.
At this point, gradient will flow to infinity. At that moment, second machine starts. At this point, you will have problem because it's a quick jump.
Okay. It's a intersect point. So it's going to.
Generally, you have power plants of 3 machines, not one. Believe me, Monte-Karlo works better. More better works genetics. I don't know, do I have time? For larger. Maybe not. BTV, what happens next week? For this one, I think